Welcome. In this video, we're going to talk about local linear approximations and differentials. So let's start with local linear approximations. Pretty much what it is we can use the tangent line of some type of curve to estimate other values on the curve. So for example, if I give you just some curve here, okay, and I find the tangent right here, so here's my tangent line, I'm going to do a little dashed. To estimate the value of this point right here on the curve, let's say it's some function which is really difficult to plug that in. If you actually plug this into the curve, I'll do that in red right here, or actually onto the tangent line. See how close those blue and red lines are from each other? So that red is the approximation of the blue. So as we get closer and closer to the actual point, the more and more accurate it actually is. So that's what's really going to be going on for these local linear approximations, is using the tangent line to approximate values of the curve, because it's much easier to plug in a number into a linear equation than it is, for instance, a cubic or a square root or anything like that. So let's look at our first example here. So it says use the tangent line at 1, 3 for f of x to approximate f of 1.1. So plugging in a 1.1 into this is going to be pretty gosh darn difficult to do, okay? But we can approximate it by finding the tangent line. So let's go ahead and do that. So I need to find the slope of this. So this is going to give me 3, actually negative 3, x squared plus 0. Okay, and I want to find the tangent line at 3. So that's the tangent line I'm making. So make sure you plug in this right here to find your actual tangent line, because you're trying to find the tangent line at this point 1, 3. So f prime of 1 is equal to negative 3 by plugging that 1 into x right there. So we're going to get y minus 3 equals negative 3 x minus 1. Okay, so this is our tangent line here. We're going to be using this to approximate the value of f of x at this 1.1. Again, I'm not doing anything with this 1.1 until the very end. I'm finding the tangent line at this point of this curve, and then once I do that, I'm going to be ready to go ahead and plug this in. All right. So when I plug this in, I'm going to do that in blue now. So this is my plugging in point, is y minus 3 equals negative 3. Now I can plug in at 1.1. Okay. So I'm going to get y minus 3 equals, that's going to be 0.1. So 0.1 is the same thing as 1/10. Easier, I think, to work with fractions in this case. So we're going to get y minus 3 equals negative 3/10. Just throw that 3 on over. So we're going to get 3 minus 3/10, which is 27/10, which is the same thing as 2.7. Okay, so if you were to plug a 1.1 in, you would get somewhere pretty gosh darn close here to 2.7. So now let's go ahead and fire this up into our calculator. I'll use my imaginary calculator because I already have everything already plugged in. And the actual value of that is going to be, if you're plugging in, is 2.669. So the error is only 0.031. So that's a pretty close estimation here. So we're not too far off. And that's the idea of using local linear approximations. So we're looking at an example where they don't give us quite as much information, that we're going to have to figure it out. So let's go ahead and use the appropriate local linear approximation to estimate the value of root 65. So the first thing we must do in this case is, well, we were given an f of x over here. We need to find f of x over here. So pretty much what we're going to do is get rid of the number, and that's going to be your function. So this is going to be the square root of x. Okay. Now, we're going to be careful about this. We have to figure out what our initial point is going to be. So before we're given 1, 3, what's a nice and easy point in here that's pretty gosh darn close to 65? The square root is 64. So let's go ahead and let x equal 64. So when we do that in our function, f of 64 is equal to 8. So now we have everything all set up as we do over here in this problem. So that's all this requires, is a little bit extra work here. So let's go ahead and find f prime of x. Well, this is the same thing, by the way, as x to the 1/2. So this is going to give me 1/2 x to the negative 1/2, which is really this right here. Just rewriting it because I'm going to plug stuff into it, make it nicer. So f prime of 64. When I plug in a 64, I'm going to get 1 over 16. So I'm going to get 1 over 16. Now for my blue step, we're going to do, actually, nope, not quite yet. So my equation of my line is going to be y minus 8 equals my slope, x minus 64. Now it's my blue step to go ahead and plug in my 65 now. So I'm going to get y minus 8 equals 1 over 16, 65 minus 64. So we get y minus 8 equals 1 over 16. So y is going to equal 8 plus 1 over 16, and that's going to be, I don't have it in front of me right now. We'll just do this. 8 and 1/16. If you plug that in your calculator, you're going to get 8.0625. So that's the approximation right here. Either one of these answers is good. All right, question like this is going to be a non-calculator, so I bet you they're going to have 8 and 1/16 as the choice rather than the decimal. I just want to show this to you what it is so that when we actually do the real value of root 65, and you can go ahead and plug that into your calculator. I'll just do it for you. It's actually going to be 8.06225. Wow, that's pretty close. So the error here is going to be 0.000242 if you just keep plugging everything in. So that's going to be the error right there. So the approximation is pretty gosh darn close. All right. So that is how you use the tangent line to approximate values of functions that are somewhat difficult to plug into depending on what numbers you have. Let's go ahead and move on to differentials. Okay, so dy and dx are called differentials. Okay, so here's a definition. Let y equals f of x be a differential function. The differential of x dx is an independent variable, and the differential of y is defined as dy equals f prime dx. Why is that true? Well, what's the derivative of y? We would call that dy dx. And the derivative of f of x is f prime of x. So this goes to reason that we're at dy equals f prime of x dx. Okay, so that's where that comes from. Now, let's go ahead and describe what everything is. I'm going to use that right on this little graph right here. So here you have your function right there. I'll kind of highlight that in blue so we know that's our function. And we have our tangent line here in red. So I'll just color that in red. It's a little bit easier to see. So if you're just picking some point on the curve over here, just some random point, the distance, the x distance, the horizontal distance is going to be delta x, which is also dx. So delta x and dx are the same. That's like super important to know. So delta x and dx are always the same. Delta y and dy, in some examples they can be the same, but more or less they're usually not the same. So the delta y is really the rise over the run part going from your tangent to your other point over here. So that's why the entire thing is delta y, because we usually say that our slope is change in y over change in x. So it's going to be the entire length, the entire vertical length from the tangent to the point. Dy is what deals with the actual tangent line. So the dy is going to be, when we get out here, the distance from that x to that height of the curve. going along that same delta y. In this case, how this is, this delta y is larger than dy. That's not always the case depending on really the concavity of the curve. We haven't talked about that yet, but it kind of matters if it's opening up like this versus if it was a curve like this. Our story would change with which one is larger. So let's get to some application parts of this and hopefully make some sense of it. And I'm going to draw this out all in this picture right here. So we're going to let y equals x squared minus 2x minus 1, which is going to be this curve right here. We need to find dy and delta y at 2, okay? And then we're going to let dx delta x equal -1, and then make a sketch showing dx delta x, dy, and delta y in the picture. So I'm actually going to first do the sketch here. So we have this point at 2. So it's going to go at -1 right here. So this is my delta x right here. So this is my x2 point on here. And then when we go over 1, well, we go over 1 right here, I'm going to be right here. Okay? So this is my delta x, and this is my delta y. All right. Now, if I were to draw a tangent line, I'm just going to kind of do a little bit of an estimate of the tangent line right here. Being red is, let's say that this right here is my tangent line. Okay. Now going from along right here, if I were to keep extending this line in blue, I would get this right here. And this distance from here to there is my dy. Okay. So again, after we go out delta x, the distance from that point to the actual tangent line is dy. The distance from that point to the actual curve is delta y. All right, so that's the picture of what's going on here. Now let's actually get to the math here. So let's find these values. So first off, dy. To find that, I'm just going to take the derivative. So dy over dx is equal to derivative of x squared is 2x minus 2. Then let's go ahead and solve for this. So dy is equal to 2x minus 2 times dx. And I'm doing everything here from 2. So dy is equal to 2 times 2 minus 2 times dx. We were told that dx is -1. So we're going to get an answer of dy equals -2, which if you were to see right here, the length from there to there is, looks like I actually drew it pretty well. That's actually going to be -2, okay, because it's going down 2. Now, the formula for delta y, I didn't touch that yet. I've only did the other one. That's actually going to come on down here. And this is a formula that you're going to need to memorize. The delta y is going to be right here. And right above is going to be our explanation for it using our definition of a derivative to go ahead and find that delta y. Okay, so you can kind of go through and figure out that, hey, f prime dot dx is the same thing as this right here because it's just the change in y. So it's just this top part of your definition of a derivative. That's my delta y. So let's go for it. So delta y is equal to, I'll just rewrite this out, f plus change in x minus f of x. Well, for delta y, this is going to be f of, and just plug everything in that we have. So x is 2. Delta x is -1 minus f of 2. So this is going to give you f of 1 minus f of 2. Which does make sense before I even plug anything in because, well, isn't that what we're going from here? Is we're doing f of 1, which is right here, minus the height there at f of 2. So let's go ahead and plug this in. So we plug in a 1 into here. and we're going to get 1 squared minus 2 times 1 minus 1 minus, plugging a 2 into there, 2 squared minus 2 times 2 minus 1. Do the final work up here. This is going to give me negative 2 minus negative 1, which is going to give me an answer of negative 2 plus 1, which is negative 1, which is something that I already knew right here just by drawing it. Okay, so this is my answer for delta y. Okay, so that is differentials in a nutshell. And it's important. These are some formulas that we're going to have to start to memorize. If you already do have this one memorized, definition of a derivative, it's just application of, hey, the top is always changing y over changing x, right? So top is changing y. And that's it.